And in this second tutorial, we will look at the second objective, which is to state when a removable discontinuity exists. That's otherwise known as a hole. So if you would flip over to our final example, example number 4, this looks like a regular rational function. So let's go ahead and attack it like we normally would. Let's find our vertical asymptotes. In this case, again, the denominator has not been factored for us. So I'd like to factor the denominator. I'll write that over here. We've got x minus 2 in the numerator. This is a difference of two perfect squares again, which factors into x plus 2 and x minus 2. Now here's where things get a little bit different. You can see that there's a common factor that can cancel away. This hasn't happened yet. I see the x minus 2 that I just factored from the denominator, and I see the x minus 2 that was given in the numerator. If you have a common factor that can cancel away, there's going to be a hole. This will create a hole. When a common factor can cancel from the numerator and the denominator, a hole will occur. Now let's keep going and see what this actually is equal to, because now there's nothing in the numerator except the 1, and the denominator is just the x plus 2. So this is really the function that we're talking about, because we took a hole away from the original. So now when I'm talking about vertical asymptotes, there is actually only one. We thought there might have been two because the degree is 2, and that gave us two factors. But because only one factor remained once I've canceled the other one out, there actually is only one vertical asymptote, and it happens at x equals negative 2, because negative 2 plus 2 would make that denominator 0. So one vertical asymptote here at x equals negative 2. Let's talk about our horizontal asymptote. I'll come back to that hole in a little bit. Horizontal asymptote depends on the degrees, and it actually doesn't matter which one you're looking at. You can look at this one. The degree of the numerator is a 1. The degree of the denominator is a 2. In this case, the numerator's degree is less than the denominator. If you want to look at this one, the degree of the numerator is 0. And the degree of the denominator is 1. It's still less. And when the degree of the numerator is less than the denominator, it will always be y equals 0 for our horizontal asymptote. So that's covering up this x-axis. Let's find our x-intercept. Our x-intercept comes from our numerator. We set that equal to 0, and of course this one doesn't make any sense. There is no x-intercept, which, again, we've covered up the x-axis with a horizontal asymptote, so there probably isn't an x-intercept. The y-intercept, I'll change to my color, my y-intercept comes by plugging a 0 in for x. So I have 1 over 0 plus 2, or rather 1/2. So our y-intercept does exist. It's 0, 1/2, and I will plot that right about here. Now let's talk about this hole. Again, this hole occurs because factors canceled. Because there is a factor that canceled away, we have a hole. And in this case, you might have thought that there'd be an x-intercept because the numerator, if x were 2, but because that canceled away, it canceled the ability to have an x-intercept. And again, you also might have thought that there'd be a vertical asymptote because of this factor, but because it canceled away, it canceled out that asymptote. So what happens is there's a hole, and the hole happens when x equals 2. And I know that because 2 minus 2 is the 0. It happens when x equals 2. So somewhere when x equals 2, we have a hole. But I need to figure out what's the other part of that ordered pair. And that's where I can plug in. I can't plug a 2 into here because I have a 0 in the denominator. I can't plug a 2 into here because I'd have a 0 in the denominator. But this fraction, I can plug a 2 into. And if I plug a 2 into this, I have 1 over 2 plus 2, which of course is 1/4. And that's where the hole occurs. There's going to be a hole at 2, 1/4. So what I'm going to do now is go to where 2, 1/4 would be and put a hole. Literally just somebody removed that point from our graph. That's why it's called a removable discontinuity. Now when I go plug into the calculator and check that everything is correct, I'm going to, let's clear this out, I'm going to plug in x minus 2, of course I'm putting that in parentheses, divided by x squared minus 4, and again I'm putting that into parentheses. Let's press graph and see that it does fit into our shell here. Now you're not going to see the hole. The calculator is smart, but it's not that smart. You won't see it in the thing. It looks like it's filled in. But if you happen to go to the table, you're going to see the error that exists. Now, let's first check the negative 2. Of course, there is a vertical asymptote at x equals negative 2, so that's why there's that error. But there is another error that happens when x equals positive 2. And you can see that right here in my output table. So we know that there is something there, but it's absolutely not a vertical asymptote because clearly the graph doesn't have a vertical asymptote here. So when I graph this now, I do have this bottom piece down here. I'll just sketch that in. I already have my y-intercept and now I have my hole. I'm just going to make sure that the graph goes through that y-intercept. And I'm going to get to the hole, of course, skip through that, and then continue on. So once again, to review, this hole happens because there's a common factor that can cancel away. I know that there's going to be a hole, and it's going to be a hole at that value that it would have been, x equals 2, and I can plug that 2 into the remaining part of my rational function to get my y value. And then I have what my hole is going to be, and I just plot that. Let's do domain and range and end behavior. X can be everything except for it can't be negative 2 because of this vertical asymptote, but it also cannot be positive 2 because there is no part of the function right here. It's a hole. So we do still have plus or minus 2 that are not in the domain. Let's talk range. Range looks like it might be pretty simple. A lot of people might be thinking, wait a minute, it's easy. Y can't be 0. And that is true. Y cannot be 0 because that is my horizontal asymptote. Everything except for 0. But there is one other number that Y cannot be. Do you see where that's going to be? This hole wipes away apart from the domain, but it will also wipe away apart from the range. That's why it's important that we figured out that it's at 1/4. The range does not exist when y equals 1/4 either because of the hole. So this is a little bit trickier of the range. And finally, our end behavior is doing the same exact stuff as all the other ones. Both ends are doing the same thing. They're both trying to approach the horizontal asymptote value, which is 1. And in this case, this is a of x. I keep changing the function name, and it's approaching 0. So thanks for watching this tutorial explaining holes, and we can practice more of that in class. Bye-bye.